All right, we're back. We are GAME 2005 in the fall 2018 semester at George Brown, and it's game physics. And it's week 10 officially, even though we're lesson 9. And we're talking about energy of a system. So this week, a couple of announcements before we move on to the lesson today, energy of a system. This week's when your assignment is due. Your assignment 2 is officially due by Friday at midnight. So I gave you guys some time to do it last week. And I told you there wouldn't be time this week to work on it because we're going to have to do things like review and other things. And then next week is your test, officially, week 11. So your test is coming during lab time next week. People who need to book extra time in the testing center and so on, please do that this week. Don't just wait till next week to do it. And we need more time for that to happen. The test will be the same format next week as it was the last time, which was true, false, multiple choice. For the most part, it'll be multiple choice on Blackboard. It'll be randomized. You'll get a cheat sheet by the end of the week that you can please print on your own. Some people won't. You also need a calculator, so please bring a calculator. I'm not going to keep mentioning this. I've kind of given you your chance to find a calculator by now. This is like week 10. So by now you should have a calculator that's scientific.
I bought a calculator just for this course because you said that mine was too good.
Awesome. That's great that you did that. So you need a calculator. You need to print your own cheat sheet. You cannot use a calculator on your machine and all that kind of stuff, or your phone. There'll be no phones, bags at the front, all that kind of same stuff that we did last time. This test traditionally, and I've done this a couple of times now, has been a little bit more challenging for some and easier for others. And I'll say it like this. More challenging for some because even though they know math, they don't know how to problem solve. So they look at it and they go, I don't know how to take this apart. So in lab today, we'll talk about some of the problems that you may be seeing on the test. Yeah.
Is it the same multiple choice pretty much?
Yes. Yeah. So basically you'll have, your questions and then you'll have to answer the right, pick the right answer. Yes.
Will the third test be multiple choice as well?
Probably not. The third test will probably be a practical test that'll get you guys to write in class together, right? It'll be more like a challenge. So you'll have a challenge. Sorry?
You mean like writing software?
Yeah. You'll probably have an hour and a half to write something that's doable, something like that, based on your assignment number 3. So if you've done your assignment number 3, then the test should be no problem. But more or less, it'll be like an exercise, for you trying to do some simple collisions, basically. That's what it'll be. With using the whole template, the STL template that I'm going to provide for you guys starting next week. So next week, remember that it is the test. There'll be no lecture officially next week. Next week, I'll be here to handle any kind of questions, concerns, those kind of things during this time frame. So Tuesday morning, that's what I'll be doing. But there will be no physical lecture because you're not going to absorb it anyway, right? So. Well, it doesn't make sense, right? So that's the problem. So, but then you'll have your test during the lab periods all throughout next week. Okay? So that's that one. So I will make an announcement on Blackboard to remind everybody because people need that kind of reminding. Hell, I needed that reminding this morning, right? So that it's come so quickly, but that's what's happening next week. And again, Friday is your assignment 2. So please, if you haven't had a chance to, I'm going to be nice, finish it, right? Some people haven't started it. Please finish your assignment, hand it in. I know I will accept multiple submissions. I will not accept submissions via email or via Slack or any other messaging system. People have sent me weird submissions. I'm sorry, I can't. I have to do it through Blackboard. So please submit your stuff through Blackboard. I mentioned it before that assignment 1, there's some parts of it that were done badly, but for the most part, people did well. Some really good assignments, some really bad assignments. But the things that I don't understand and I really can't accept are things like I have to use like a microscope to see what you're writing. Okay, your writing is so bad on the assignment that I can't figure it out. Right? You took a picture of it with your phone, but you took a picture of it in low light, and there's so much shadow on the page that God help me to try and figure it out and do some kind of parsing with a graphic manipulation program. I don't have time for this, guys, right? I don't have time for post-processing your work, right? So please make it clear. Make it easy for me to mark your stuff. Make it sure that the assignment looks good. Like if you're going to take a picture, it's fine. I recommend you use some other tools, you know, but scan it. Go to the library, scan your stuff in, and that might be better, right? You know, something like that if you're going to do it. But yeah, there's some people that have lost are going to be, you're going to see your marks. There's lost marks basically because I just can't see it, right? And that's bad. So what else? I think I covered most of everything. Oh yeah, MIGS. MIGS is something that's happening next week, which is kind of funny because your test is on starting Tuesday. So I'm not sure if anyone can make it to MIGS. Montreal's international kind of gaming show, I think is what it is. Let's take a look at that really quickly. I'm not associated with MIGS at all. Yeah, Gaming Summit, there it is. But there's some really cool things at MIGS that you guys should take a look at. They've got a lot of networking. There's all kinds of sessions you can go towards and meet people in the industry. It's in Montreal, so there's a bit of an expense, and it's November 12th to 13th. So a couple days, I believe that's the weekend, yeah? Isn't it? Or is it Monday, Tuesday? I can't remember. Is it Monday, Tuesday? If you're going to go to MIGS, seriously, if you're going to go to MIGS and your test is on Tuesday, I will move your test. I'll do that for you. Like if I'm not going to kill you and say, go to MIGS, but you get 0 on your test, right? So yeah, please let me know if you're going to go to MIGS and you're going to do your test on, if you need to move your test on a Wednesday or Friday, I'm okay with that. This coming up thing, because I think it's important for you guys to go to conventions and shows like this, because being a game developer, one of the things you need to do is market yourself, right? And I really believe that it's important to go to MIGS and stuff like that, right? So, yeah. Okay, so that's it. Anyone else have any questions before we continue? So today we're talking about energy of a system, and this is interesting because it takes a different approach to what we've talked about before. So we have some stuff that we've been able to solve with Newton's laws and so on, but this is a key concept, energy of a system, when it comes to collisions. Actually, this is a good lead into collisions because, think about this before we move on. You have some kind of energy that is being transferred, right? One of the things that we know is from physics is that in the universe, energy cannot be created or destroyed, right? That's the kind of almost like a central precept nowadays. So you can, but it can't be destroyed. Like I said, it can't be created or destroyed. So you can transfer it, translate it, convert it. Some of it can be lost and moved somewhere else, but it can't be destroyed or created. But so energy is transferred. So think about this idea of the collision that we're going to be talking about following next week. You have this energy that is, momentum, if you will. Cars traveling at a certain rate of speed, and then it has this energy that is built up. The faster the car moves, I'm looking at a car as an example, it builds up energy. It's actually holding something called potential kinetic energy that's inside of it. The faster it moves, the more potential kinetic energy it has, right? More and more and more and more. And then finally, if something stops it, like a wall, right? Where's that energy going to go? Some of it's going to go into the wall. Some of it's going to be reflected back, right? Some of it's going to be lost. When I say lost, it means it's going to be transferred into heat, smoke, all the other things that can happen to it. So there's a lot of energy that's, and sound. That's part where the energy goes to. There's a lot of sound and so on. So energy has to go somewhere. And when you do collisions, we're going to be talking about 2 types of collisions: elastic collisions and inelastic collisions, right? And the difference between a rigid body, right, and a soft body. All right. So now in this course, we can't talk too much about soft body collisions and soft bodies in general because it's kind of out of scope. Soft bodies would be things like liquids, sloshing around, that kind of thing, right? Fire, chemicals, those kind of things, right? Whereas, sloopy, droopy jams and slimes and those kind of things, right? You could have these soft bodies, things made of rubber, and irregularly shaped objects. Here we're really simple. All we're talking about is regularly shaped, objects that have center of mass in the middle of them. They're not like imbalanced or anything like that, and they're hard bodies. They're going to be deformed a little bit, but they're not going to be, they're not going to turn into soft bodies or blow up. We're not going to calculate the explosion. Put it that way. Okay. So again, we talk about energy here, and energy is defined as, and this is really cool, the capacity for doing work. Capacity for doing this. The more energy we have, the potential for us to do work is greater. That actually makes sense too. You get up in the morning, you have your coffee, feel like you can do some work, right? You get some energy. So again, there's this idea of energy, work, and force, and how they're all intra-related in some way or another. All right, so again, work, when we say work, the capacity to do work, which is energy, also is expressed in joules. Now, this is where we get, megajoules, all of these kind of things. There's two types of energy: potential energy, so that's we usually assign a U for that, and kinetic energy, which we usually assign the letter K for that part. There's other types of energy that we can't really cover in this course: mechanical energy, chemical energy, thermal energy, nuclear energy, radiant energy, electrical energy, gamma radiation, the stuff that makes the Hulk, things that that maybe exist in the universe that we have no idea about. Other kinds of energy, maybe even gravitic fields, which we have no idea work or not. But yeah, we don't cover that crap in the course. All we cover is really kinetic energy more than anything else, because really we're talking about kinematics and mechanical energy that we're going to be talking about more than anything else. So mechanical energy is the idea of energy, how to move something or reposition something. Again, potential energy is the energy of position. It's an interesting way of thinking about this. And kinetic energy is the energy of motion. All right. So, and then if you think about mechanical energy, that's both. If I have both position, energy from a position, and energy from motion, I've got something called mechanical energy, right? So how does that work? So again, we want to use the particle like we've done in the past. We've been using the particle, which is a model, right? It's not realistic. The stuff we've been doing is, we get semi-realistic motion with the particle, but we don't have, again, irregular masses, this kind of thing. It's very simple motions that we're talking about right now, okay? So again, we're going to be talking about systems. What's the difference? What is a system, and different ways of storing energy, okay? So think about this: is a system is almost like a small container or a small portion of the entire universe. All right. So when I look at a system, I'm talking about things like, a collection of objects, a region of space, that kind of stuff, some kind of small area that I'm looking at. And usually a system is made up of almost like a small snippet of reality. Okay. So I'm looking at something. I have it in my lens. Things I can see in my camera in the game world, that's the system that I'm looking at. I don't care about the other things outside the system. I'm just looking at that thing, right? I'm not interested in how my system will affect larger systems and how, as an example, it's going to impact the Earth, and the Earth is going to impact, the rotation of the moon and blah, blah, blah. There's no parenting here, and there's no, inverse kinematics of this system. It's just literally just the system that we're looking at. Okay, so again, a very simplified view. So we have this idea of the system, and we'll have part of our system having a system boundary. So things that we want to talk about in the system, and anything outside the system, again, mostly we don't care about it, okay? So here's an example of a system. The system is the object. Its surface is a system boundary. The force is an influence on the system from its environment that acts as across the system boundary, right? So some kind of influence on the system. We're influencing the system, whatever it is, the container that holds all the objects that are in the system. We're influencing it by some kind of energy. All right, that's what we're doing. Okay, work W is done on a system by an agent exerting a constant force on the system. And this is a product of the magnitude F of the force, all right? And what we're trying to do is we're using force right? To do some work on a system. That's what's happening, right? So that's what I want to talk about. So think about work being the amount of force with, you know, and it says delta R, right, which is the range. So that the amount of displacement cos theta. That's interesting. So imagine here, this is what we're talking about here is we have displacing force. We have a system, so some kind of, let's say the cube is a system. Anything inside the cube we don't care about. It's inside the system, right? All we care about is the boundary of the system, which is the cube's, you know, boundary. The cube is the bounding box, if you will, for the entire system. Okay, and if you think about that from a physics or game perspective, if the cube is a bounding box, inside the cube you could have an animated character. All right, let's go back to that for a second. Some people may not understand. So what's the difference between locomotion and animation? We have two different things, locomotion and animation. Guys, anyone have an idea? Locomotion and animation. I'm going to start asking people because I can see people that are paying attention. Uvo. Yeah.
I guess locomotion would actually translate the animation to around the space rather than just finding a motion in place.
Okay, so difference to translating an animation is locomotion. Anyone else want to kind of add to that or change that definition? Come on, guys. Yeah.
I guess in the same vein, it's like you can have an animation that's running, but it's not actually exerting force in any kind of way, so you could be running in place.
Okay, running in place, like Uvo said, yeah.
Yeah.
All right.
So I'm assuming locomotion is the actual, you know, if you have a character that kicks off, it's actually exerting a force and pushing itself forward.
All right, some kind of, you know, forward kinematics or inverse kinematics. Okay.
I guess locomotion is movement that's actually being caused by a force somewhere in the system, and animation is just sort of movement that's just being caused by nothing whatsoever.
Yeah, I like to think about animation as something that's happening inside the system. So think about the system itself, the bounding box of the cube we're talking about. Let's say there's a character in there, right? And there's animation taking place to show a realistic movement, right? But the animation has no effect typically on what's happening, right? I mean, you can make it effective if you, in Unity, you can actually, you know, kind of check mark something that says, you know, move along the same, you know, rate as your animation kind of thing, right? But really locomotion is where I'm moving in a system and, you know, with, you know, that's contained, maybe there's other objects in that system. I'm moving the system around, right? Locomotion, I'm moving something around. Animation can be happening inside the system, but I'm moving the system around. So there's a difference between animation and locomotion. So here, think about this. I've got this system. There's a bounding box. There's a cube. And I'm exerting force on the system across some kind of distance. Locomotion, right? Cos theta, because it depends on where my force vector is going to be, you know, kind of directed. If I have my force vector directed upwards, I'm going to be losing efficiency, right? The more energy I'm putting in a different direction. Remember, that force vector is made up of X and Y components, right? Some of my energy on the X-axis, some of my energy on the Y-axis in this particular case, right? So I don't have all my energy directed in the direction I want my system to, you know, to move, right? I want my system to move forward, but I have energy moving up, right? I'm going to lose energy going forward. So this is where the cos theta comes in, right? Here's something that's really key. A force does no work on the object if the force does not move through a displacement. So even though I'm exerting a lot of force, imagine if I have some kind of friction, right? Let's say static friction, and I'm pushing on an object. I'm pushing an object. The Hulk is trying to move an entire building, right? And he's pushing into the building. He's pushing at it. It's cracking, but he hasn't done any work, right? Until he moves that entire building, which chances are he's not going to move because the Hulk isn't that strong, right? Chances are. You know, he's probably going to crack the building. He'll probably destroy the building before he moves it. Whereas someone like Superman, right, it was another level of scale in terms of superhero, right? Maybe he's going to use his, you know, laser vision to kind of like, you know, carve out the building from the surrounding cement. I don't know, the asphalt. And is he going to move that entire building? Because Superman's on another scale. He's like, or more godlike. If Superman moves the building, right, maybe the same size as the Hulk, he does work. But the Hulk, no matter how much he strains, even if he puts a lot of force into, cracks the whole building up, he hasn't done any work, according to physics. Okay, according to physics. So again, So it says the work done by a force on a moving object is 0 when the force applied is perpendicular to the displacement of its point of application. So the force up, as an example, the force perpendicular means the normal force, right? Think about this normal force that's going up, okay?
Like carrying things around never really spends any work or is work.
Well, if we're carrying things, is it part of my system? That's the thing. See, you know, it depends on how you think. If you see things, if you see the object that you're carrying is now parented to the system, it's part of, like, you know, the child of the system, then yeah, no, there's no work being done locally, right? However, if you're pushing something that's a different system, then yeah, you're doing work on that. Yeah. So I'm not trying to confuse you, but I know there's going to be questions. Go.
Yeah.
It depends is the answer. That depends. So you have to kind of figure that out. So if you're trying to move something, as an example, and you're moving something that's outside of your system. So there's two systems. One, you have a bounding box for your system, and there's another one, right? Another system that's apart from yours, and you're trying to influence that system by moving your system or using your force on another system. That's totally different. Example: the Hulk in a building. The Hulk is force, or is trying to exert force on the system that is the building. The building could contain many levels, many floors, right? It could have secretaries running around and bosses drinking coffee. You know, they're inside the system, but the Hulk is pushing this entire thing, right? So that's the system, right? But the system could also be, if you take another time slice, the system could be the Earth, right? And if Superman, I don't know how he would do it, or if some kind of crazy guy like Galactus, right? We're talking about another galactic level, you know, entity is pushing the Earth could be the system, right? It really depends on what time slice, what are you trying to do? What are you trying to calculate? Like force on what system? So again, we got to think about things like, you know, when it says what it says here, force applied to a rigid object that can be modeled as a particle, the displacement is the same as that of the particle. So if I move the whole object, it's a rigid body, right? Then the displacement is based on where we calculate the particle to be. And usually the particle is the center of mass. Okay, so if I look at a person, the center of mass is just around their hips, something like that, right? So if I move that person, that's where their center of mass is going to be. I look at the particle as that's where the center of mass is, not at the bottom of their feet typically, all right? Although it could be modeled that way. So again, for a deformable system though, that's not a rigid body. Like we talked about soft body systems or whatever, the displacement of the object generally is not the same as the displacement associated with the force applied because the system is deformable, right? We're not talking about that kind of system in this course, okay? Just in case, for completeness, it's in here. All right, so here's an example. The normal force and the gravitational force do not work on the object because, take a look, cos theta, if cos of 90, that's equal to 0. And 0 times any displacement, doesn't matter how much you displace, so whatever, is 0, right? So the force going this way, there is no work that's being done right now because the normal force is holding up the object on the ground. As an example, there is no work that's being done. However, if I drag an object across the table and I exert some kind of force in a particular direction, then there is some kind of force that's acting on this system, this object, as it moves to the right. So this is interesting. The sign of the work depends on the direction of the force. That's pretty simple. So we've been using that kind of thing already, right? One thing to note is work is a scalar quantity, so it's not a vector. So it tells us the amount of work that we've done, right? So force is calculated. Force is a vector. Displacement is a vector because we have some kind of, and we're using r, the change in r, which is what we're using for displacement. But the final work is just a measurement of how much energy has been, supplied to the system, if you will, right? So think about this. Unit of work is a joule. 1 joule is equal to 1 Newton. And times 1 meter, which is kilogram meter squared times second squared. So 1 joule could be a Newton meter, so to speak. 1 joule is a Newton meter. that's interesting. If you think about Newton's force, meter, distance, force over distance. That is what work is. Okay, work is force over distance. If you think about that. Okay, if there's no distance, there's no work. All right, so we think about work as an energy transfer. So we have this energy and we're transferring energy from across the system boundary. So we have some kind of system boundary and we're transferring energy from one system to another. So again, going back to the Hulk or Superman example, Hulk is pushing a bus, right? Let's say in this case, he can do that, right? He's strong enough. He probably can lift 100 tons, but not 10,000 tons like a building or something, right? So he's pushing, this bus, right? Sideways. The bus is skidding. Hulk is one system. The boundary of his system is probably his hands. The boundary of the other system is where the bus. If you draw a bounding box around the bus, right? He's pushing the bus, and he's transferring energy from his system to the bus's system. Okay, that's what's happening. There's an energy transfer going on. Okay. All right. I'm not going to talk about the scalar product of two vectors. You guys should know what that is. But one thing to note is that vector A times vector B is also equal to AB cos theta, right? Where theta is the angle between A and B, right? So applied to work, what this means is that work is force times the displacement vector, the change in displacement. And that's really what it is. We're multiplying those two things together. All right. We talked about work enough. Power. So power is to measure how long it takes to apply the work. So work, energy transfer. It's newtons over meters. Or how many meters, as an example, did I move something with force? Okay, that's what work is. But power is how much work I've done over a certain time. Okay? So this is interesting, and this is where people get messed up about it because they're like, wait a minute. Power. And then there's work, and power relates to work, right? So power is a measure of joules per second or watts. And now we're getting back in, now we're talking about electricity almost, right? Joules and then watts, right? And then we're going to eventually with electricity talk about amps, right? And anyone know the difference between, wattage and amperage? It's interesting. Yes.
Watts is joules per second, right?
That's what it says.
Yeah.
And what's amperage?
And amps is current.
Right. So it's how much. I always think about, watts as how much energy there is, right? Or power that I have. And amperage is almost like the highway to kind of transfer that power, right? It's almost like a larger pipe. Yeah. It's almost like amps is almost like how much pipe do I have? Like, how much I have a hose and there's a lot of energy, right? But my hose, if my hose is small amount of amperage, right? I'm not going to get a lot of power at the end, right? Because I'm limiting them. I'm limiting how much power can go through. It's almost like I'm squeezing the hose. But if I've got a lot of amps, that means I can really, kill somebody, right? With my energy. Okay, so power again is equal to work over time. All right, so work done by a varying force. Sometimes what happens is you have a force that is not constant. So we don't have a constant force, right? And the work equation up above cannot be used to calculate something with a varying force, all right? And again, what this is talking about is for all intervals, if you think about this, work is the sum of all initial x's to final x is almost like this difference, right, of the force times, the change in direction in x, right? So why did we bring this up? Because when you think about it, if you boil it all down, it's really an integral, right? Remember we talked about the area under the curve? There's where work comes into play for varying forces. So I have different forces, different amounts of force that I have over time, right? And instead of me trying to figure out things by little slices of the rectangles across under the curve, you can use integration to figure this out, right? Will I make you do integration? For this part, you'll see there's some parts that you may have to use it, okay? work done by multiple forces. And what this is, let's say, for example, I have two forces that are exerting, this external force on a system. And if I have two different forces acting on it from two different directions, then I take, I use the components of those forces to calculate the new energy, the sum energy, the sum of all energies going in a certain direction. Oh crap! Sorry, I just forgot. I just remembered that I didn't put my parking pass in my car. See what happens when you talk about forces? It just pops into your head. First, I talked about stuff. I'm going to get a ticket for sure, right? Anyways, let's continue. I'm just going to move through. Okay, work done by a spring. So springs are interesting because, and we've talked about them briefly before, but we're going to talk about more in this section. So we think about work that's being done, okay, so by a spring. So a spring has, almost like an equilibrium point, right, where the spring's naturally going to, be seated. So think about this on a frictionless surface. When, like it says, x is 0, this is the kind of the stable state or the resting state of a spring. If I pull a spring this way, right? So I pull a spring back. The spring has a force that's going to try and put it back into its normal shape, which is this one. All right, it's going to try and pull it back this way. So the force of the spring is going to be basically, pulling a spring back into its original shape. This is a spring that's deformed, right? It's interesting because we can use springs to kind of mimic deformations, if you think about it, right? So you have some kind of car, you have different parts of a vehicle you chunk up into different sections, and then you have a spring that's inside the middle of it and is chugging along, and hit something, and then the car just does one of these, right? It deforms. And then if you think about it, that's in a lot of ways what's happening here, right? The third thing, which is I'm taking the natural shape of an object and I'm compressing it. If I compress the object, it tends to decompress back to its original shape, right? That's what it wants to do, unless the deformation is so much that it's lost its original shape. A good example of that is when we put tension on a bar, right? So imagine, again, I'm going to go back to the Hulk, right? A Hulk, they put him in the supermax prison, right? But he's too strong. So he goes to the bars and he deforms the bars of his cell, right? Until they've changed shape. The bars want to spring back. Truly, they do, but they can't, right? Because he's literally changed the shape of these bars until, and they don't have the elasticity because they're rigid objects to spring back, okay? Whereas a spring has this elastic property as well, right? The spring has a form, and then when it's displaced, like I said, it wants to go back to that original form. And it's done because of the shape of the spring itself, okay? So there's compression, and then there's elongation. So when I elongate a spring, it wants to go back. When it's compressed, it wants to go back. And the shape of the force, I'm going to say the shape of the force here, is opposite to that of the deformation. So if I elongate something, the force is going back the other way, right? If I compress something, it's pushing out, right? And that's where the nature of the work is being done. Okay. So again, here is now this is interesting because we have Fs. I don't like this because Fs also could mean static friction, right? So be careful when you look at this. And we have this minus kx, right? Minus k. When we look at this thing, and by the way, we're talking about Hooke's law here. Minus k is the spring's constant, if you will. Think about this as stiffness, right? So k is the stiffness of a spring. The more stiff a spring is, the more it's going to take, more energy it's going to take for me to deform the spring. So think about, again, a car. If we can think about a car as a type of spring, the stiffness of a vehicle or something that's a rigid body is very, very high, right? So the deformation is going to take a lot more energy for me to deform that vehicle, right? Now, nowadays, vehicles are really not that easy, not difficult to deform because they're all made of fiberglass and stuff, right? And actually, there is a set of mechanisms in the car that it will deform easily, right? So that it absorbs the energy as opposed to transfers it to you, right? Yeah. But think about this, the idea of a spring and stiffness, this, value K, which is the spring constant, Hooke's law, right? Basically says that the force of spring is equal to negative Kx. So where X is the direction of the energy, right? So if I want to displace something this way, then the force is going to be the other way, right? That's why it's a negative Kx, okay? Okay, let's keep looking at this stuff. So the Hooke's law is, again, the force vector for the spring is equal to the initial force, right, on the x-axis, which is equal to negative Kx initial, right, whatever that initial force is, okay? Again, it's just saying the same things. We've talked about this. One thing I need to talk about this. The spring force is sometimes called the restoring force, right? Because basically it's going to restore it to its original shape. One thing we know is that springs tend to oscillate. So yes?
On this thing you're showing us, the force of the spring changes linearly, but would there be a point where it sharply increases when it can't naturally stretch or compress anymore?
Yes, there is that too. But again, we're trying to talk about it in its most simplest forms, right? Otherwise, we're going to go crazy with it, right? We can, once we start talking about 3 dimensions and stuff and how a spring can like deform this way as opposed to just this way, right? And we're in trouble. Okay, so one thing to know is that when a spring is released, it goes through this oscillation. It doesn't go back and stop. It's not like I stretch a spring and it just goes back to its normal shape. It goes kind of in and out of oscillation until it reaches equilibrium again. All right? All right. All right, so here's an example of work done on a spring, right? So we calculate this by, take a look at all this. And it's integration, right? Now, this is interesting because we did a Spider-Man question last assignment that talked about, is it realistic for Spider-Man's head to keep bobbing in and out, right? And of course, it's not realistic. It's not realistic because there's going to be, the restoring force is going to put Spider-Man back to equilibrium. That's what's going to happen, right? Or so we hope. So you can see that you can use these integrals. We can say the work done on a spring is the integral of the force of a spring, right? Times the change in displacement, right? That's what's happening. That's the integration. When we can say that, and once we have this, this is an integral from x initial, the initial position, to the final position, times negative kx initial, right? That's what this is, times, the change of x initial, which is the displacement, all right? So that's really what you can think about. So if you did that, you get to this idea that work of a spring is, once we've gone through all this stuff, is equal to 1/2 kx squared, okay? So it's interesting that they came to that. This is the proof that how they do it, right? So kx squared max, the maximum displacement of a spring. That's the maximum work that can be done, right? So where we have k is the spring constant and x is the total displacement. And that's going to equal the maximum work that's going to be done by the spring. And then the net work done as the block moves from the maximum position, elongation, to the minimum position, which is also negative max to positive max. Negative max would be the maximum point where the spring can move before it breaks, okay? And the maximum point where it can be compressed before it breaks. You can still break a spring, crack it up or whatever, right? So negative x max to positive x max, you have this total oscillation range, if you will, right? And that's the net work done between those two variations. And you can see that in the graph here, okay? So positive and negative forces. All right. This is just repeating some of the same stuff. Okay, so I'm just kind of going through it. All right. A spring with an applied force. So you have some kind of force applied on the spring, and then you have this, the force of a spring coming back out. So if I have a system that's attached to a spring, right, and I've applied force to a spring to compress it, then it's going to apply force in the opposite direction on the system that's that's there. So example, if I put a block on the system, and then the spring will push it back out, right? Potentially, right? So if the applied force is equal and opposite to the spring force, right, then we can say that the force applied is equal to the negative of the force of the spring, which is a negative spring constant times the x initial, right, which is just the spring constant times the initial displacement, or the total displacement, if you will, right? Okay, so that's what that is. Again, we're just analyzing that. Does everyone understand this part? So this is where we actually apply. So when we compress a spring, it gives us force back. We're going to see this again. So what this is basically saying, hey, look, I've got this force, and it's going to push me back the other way. That's what's happening. Okay. All right, now this is one of the keys of this course. If you're going to learn any kind of learning outcome, this is one of the learning outcomes from this course we have to know about, something called kinetic energy, all right? So it's a possible result of work. We're influencing a system, and we want to give it some motion, right? Remember, work is Newton meters or joules, right? We're pushing something to move, right? And kinetic energy is the energy of a particle due to its motion. So we have K, which is the kinetic energy, is equal to 1/2 mv squared. Now this is kind of a key, right? Where K is the kinetic energy, m is the mass of the particle, and v is the speed, right? So mass times speed, right, squared, that relationship gives you some kind of kinetic energy. And if you think about this, if mass is in kilograms and v is in meters per second, kilogram meters per second, right, is what we're talking about, right? A change in kinetic energy is one possible result of doing work. I like this as we transfer energy to the system. Did I skip it? Okay, there we go. Calculating work. Okay, so I've got this external force, work external, is equal to the, again, this is the proof of how this works, right? So we have the integral of the initial x position and the final x position is the sum of all forces times the change in x, right? And then when we break it down, it comes out to work external is equal to 1/2 mv squared, right? And it says, now it says mv squared final minus mv squared initial. That's what this is. So the total displacement, if you will, the total change. We can say that work external is equal to kinetic energy final minus kinetic energy initial. And my friends, this is a key equation because you can sit there and say, okay, once I know that I have my initial kinetic energy or my final kinetic energy, whatever that is, if you're given that, and the initial kinetic energy, that's the change in kinetic energy, right? But if you know that that's the case, you know what work is. And we know also that work is Newton meters, which is force, right, over distance, right? So you can make that, relation between one and the other. So again, we have this displacement in x. We want to have the sum of all forces to push this mass from with the velocity initial and the velocity final, and that is the total change in x, and that is the kinetic energy that we're going to be, relating to the work that's being done. All right. Yeah, I'm sure. So I'm just make sure it's there. Okay, so we have this relating work to energy. Again, this is a very important slide. We have initial energy plus work is equal to energy final. All right, so we have some initial energy, right? Whatever energy of a system, the energy of a system has a certain amount, whether it's zero or not. Think about this for a second, right? Again, the bus, Hulk, bus is sitting there. How much energy does that bus have? None. Hulk is, so energy initial for the bus, 0, plus work that's being done by the Hulk is equal to energy final, right? Or the bus is moving in a certain direction. Hulk is pushing it to move faster, right? Energy initial, the bus is moving. Hulk adds energy, energy final for the bus, for the system, right? Or the other way around, yeah. Or Spider-Man is trying to slow down a train, right? Here's the example, right? The train has initial energy. He's on the tracks, or even better, Mr. Incredible, like the last movie, right? Mr. Incredible is trying to slow down a train, right? And the energy initial is going in a certain direction. He's applying work in the opposite direction. Then you have some kind of energy at the end. Is it enough to stop the train? We don't know. Maybe it is. Maybe he'll just hang off of the train at the end, like he did in the movie. Energy can either be potential or kinetic, and this is really, really important as well. So remember, we have kinetic energy and potential energy. So remember, potential energy has something to do with distance or displacement, position, right? Kinetic energy has to do with movement, right? And if you can say that my kinetic energy plus my potential energy plus all the work I'm doing is equal to the kinetic energy final plus the potential energy final. This equation is almost like a balanced equation if you think about it, right? So kinetic energy initial plus potential energy initial plus any work is equal to the final stuff. All right, so positive work increases energy, right? Negative work decreases the energy. So negative work would be if I'm the Hulk or Spider-Man trying to slow down a train, right? Negative work I'm trying to do, right? Train's going a certain direction. That system is traveling in a direction. Work is being applied in the opposite direction. That's negative work, right? And then what I'm trying to do is slow down the system and see if there's going to be zero energy at the end. So no, where's the energy being transferred, right? It's going to be eventually there's going to be enough energy going to be lost in terms of noise, right? Because Spider-Man or whoever's the superheroes trying to slow down the train, right? There's noise, there's friction, there's heat, all those kind of things. That's where the energy is. Probably smoke too. All that energy loss is happening in the train, right? Okay. Again, when we think about this, positive or negative work is determined by the angle. And recall that work is equal to force times the displacement cos theta. Again, notice it's S now, not R. Don't be fooled by this. S is displacement, so is R range, right? Whether you see it one way or the other, you should understand what this means. It means displacement. Okay. So the work kinetic energy theorem, here's the one that we need to know. So again, work external is equal to kinetic energy final minus kinetic energy initial, which is the change in kinetic energy, okay? And we're going to continue because we've talked about this to death, right? The net work, is equal to the change in kinetic energy. Again, we could also say that is kinetic energy final minus kinetic energy initial, all right? So example, what is the net work required to accelerate a 3 kilogram object from 2 meters to 4 meters? How do we find that out? Well, we know what's work, right? What is work? Force over mass, force over distance, right? So I have a 3 kilogram object, right? And I'm going to accelerate it from 2 meters to 4 meters. So how do I figure this out? What other equations can we use here, right? So kinetic energy, right? Let's go back up. Let's go back up the chain here. All right. So when we look at kinetic energy, we go back up the chain. Let's see what it says. It's work can also be calculated, or kinetic energy can also be calculated as 1/2 mv squared, right? 1/2 mv squared. So remember that kinetic energy final minus kinetic energy initial is the total kinetic energy we need, right? So if we go back to this question, right? And it says, what is the net work? 1/2 mv squared. So a 3 kilogram object from 2 meters, right? So 3 mv squared. V squared is 2. 3 times 4, right, is 12. So we have 12, and then we're moving to 4 times 4 is 16 times 3, which would be that's the final, right? Is what we're moving towards, and that's how you take the 1/2 mv squared for this one and 1/2 mv squared for this one, and you get the change in kinetic energy, which is the net work that's being done. Does that make sense? Yeah. Okay, potential energy. What the heck is potential energy? Think about this. It says it's determined by the configuration of a system in which components of the system interact by forces, and the forces are internal to the system, okay? One thing that we know also is that we have this work kinetic energy theorem example, right, that we talked about before. I'm going to go back to that potential energy in a second. But we have this example where we have the block, right? And we're pushing the block. The normal force and the force of gravity is being zeroed out. And if the block is on some kind of frictionless surface, so we don't care about friction at this point, and we're applying force to the block, again, we can say that the external force is the change in kinetic energy, right? Which is 1/2 mv squared final, right? Minus 0, because originally there's no force, there was nothing. Remember, it's kinetic energy initial, kinetic energy final minus kinetic energy initial, and that is the work that's being done externally to the system. The initial energy was 0, so all we care about is the final energy, which is 1/2 mv squared. Okay. All right. We want to talk about potential energy, and one of the things we want to talk about is the displacement of an object, the potential of displacing an object over time. Okay. So example, I have this other example, Hulk, right? He lifts a bus over his head, okay? Initially, the bus, sitting on the asphalt has no potential energy. It's on the asphalt. There's nothing that you can move, especially if it's a long, flat plane. Chances are there's nothing that the bus is going to do to fall through the street, okay? Chances are. But if Hulk lifts the bus over his head, right, now that bus has been given potential energy, right? Hulk has transferred energy potential, right, by lifting the bus over his head, because if he lets it go, the force of gravity is going to pull that thing down and smash the bus down on the ground, right? So you can impart energy to a system by changing its displacement, right, by lifting it up, right? And a lot of times it's done by gravity. By the way, potential energy is a key when it comes to things like displacement in terms of thermodynamics, all kinds of crazy stuff, right? Things like, the pressure that you see at the bottom of the sea and all this other stuff. It's all because of gravity, right? And we'll talk about that later on, maybe. So I got this book. So here, the physics book is lifted above the table. Because depending on the height of the table, I'm going to get potentially more velocity happening. So because there's more velocity, that the book is going to fall with, I have this potential energy, right? And really what we can calculate is the vertical displacement of an object, whatever that is, okay? And what we talk about this is it's storing energy. So the Hulk example with the bus over his head, as an example, he stored energy in that bus, right? Because what's happening is he's used his energy, his strength energy, to push the bus up over his head, right? And it's transferred into the bus, it's stored in that bus. Until Hulk puts that bus down gently, right? That bus has kinetic energy, right? It's going to fall, or potential energy. All right. So we have the first type, which is gravitational potential energy, which is something that we can have, right? And it's just the energy associated with an object at a given location above the surface of the Earth. The higher it is above the Earth, the more energy it has. Okay, that's what I want you to think about. Okay, so we can say that the work external, right, is equal to the mass times gravity from a y-axis final minus mass times gravity from the y-axis initial. All right, so what this means is if I have some kind of y-axis initial, it's way up here, and I have some distance is going to fall, right? You're going to get an external force, some kind of external energy. It's going to build up. All right. So what we want to look at is the potential energy. Remember, U is potential energy and K is kinetic energy. The potential energy of gravity is equal to the mass times gravity across the y-axis, whatever that y-axis is. Units are, again, stored as joules, and it's a scalar. Okay? Okay. I'm not going to go too much more into that. Vertical height is the thing that we're talking about, and of course, we have to think about this frame of reference. All right, so we've talked about so far, up until now, we've talked about things like work and energy. And again, just a quick hit. What is energy? Right, it's going back to the beginning, the first slides. I can't continue without this because we're going to get into trouble, right? Yes?
The capacity to do work.
Capacity to do work, okay? So if energy is the capacity to do work, right, and work is defined as? Come on. It's force over distance, right? Work is force over distance. So if I try and move something and I don't move it, how much work is being done? Even if I spent a lot of energy doing that, how much work? 0, Doesn't matter. At the end of the day, right? It doesn't matter. And you know what? I like physics in some ways because it's kind of esoteric. It's got some kind of meta, kind of thing around it, right? If you think about this, it's almost philosophical in some ways, right? No matter how much you try, if you don't get it done, at the end of the day, your bosses don't care, right? No, I'm serious. Think about this in a real case scenario. You can try really, really hard to get something done. You try and work on a game, but it never gets finished, right? You do work on an assignment, but you don't hand it in, right? At the end of the day, right, you still get zero work for it, right? So that's the way it works. And it's kind of philosophical in some ways, but it makes complete sense if you think about it from a physics perspective. All right, so now we get into this idea of elastic potential energy. And usually it's associated with a spring, okay? So springs are a great mechanism for figuring out potential energy. And it's always based on the spring constant. So remember that this spring, the force of a spring is equal to negative kx, where k is the spring constant, x is the displacement of the spring, right? So the work done by an external applied force on a spring block is defined as this, the final minus the initial, right, as an example. And the work is equal to the difference between the initial and the final values. All right, that's what it is. And that's the potential energy that you can have in a spring. So what does that mean? It means when I've pulled the spring, right, out of its natural comfort zone, right, the natural equilibrium, I have, until I let it go, there's potential energy there, right? If I let it go, then the energy is transferred from potential energy to kinetic energy. There's an energy transfer. It becomes something different. I store energy when I use potential energy. I release the potential energy. Now it transfers into kinetic energy. And now it's kinetic energy that's flowing, right? I push a spring, right? It has potential energy to push back, right? When I let the spring go, it's going to flash back right at me, right? So there's potential energy stored in there that's going to be transferred to kinetic energy. And this is a really interesting graph that comes from the book. I think I broke it down into further parts below. Did I? I did. So here's how it looks. Okay, here's the bar chart. So look at in this case, the spring is in equilibrium. Kinetic energy is 0. Potential energy is 0. Total energy, 0. Nothing's happening, right? I don't have anything here. And when I push the spring, as an example, so I compress the spring, or I pull the spring, doesn't matter which way, one way or the other, potential energy they have some energy. The total energy of the system, because I've transferred energy from my hand, into the spring, from one system to the other, an elastic system, right, to an inelastic system. I have an inelastic system, me, and I'm pushing energy into the spring, right? And I've transferred energy in the form of potential energy, right? Until it comes to the maximum level that I can push the spring, until I can't push the spring anymore. And now the energy is maxed out. See that? Where the chart is at its max. I'm just going to zoom in here a little bit so you can see that. And this is a kind of a key learning, right? So I start pouring energy into the spring, and then I pour the maximum number of energy into the spring until it's fully compressed. Okay, and I've got this total energy happening here, right? So there is elastic potential energy in the system, but there's no kinetic energy yet. All right. And now I let the spring go. I let the spring go. So what's happening is potential energy is transferring over time, right, to kinetic energy. That's what's happening. Starts off as all potential energy, ends up as all kinetic energy. And then what's going to happen is this bouncing back, right, rebound that's happening with the spring, this oscillation back and forth until the spring comes to rest, okay? So it's interesting. That's the other type of potential energy. So far we've talked about two potential energies, gravitational potential energy and some kind of elastic potential energy from a spring, okay? All right. This idea of internal energies is really, really important because the energy being transferred around is not external, but actually internal, right? So I transfer energy from an external system, work external, to an internal system. The system itself is going to store the energy, right? And then when it has this pent-up energy, it's got to do something with it. It's like the Flash. By the way, there's different theories about the Flash. I'm a comic book guy for some reason today. I don't know why, right? Just today, right? Flash, he uses the Speed Force, yeah? If anyone knows about the Flash, he uses Speed Force. Some people say that the Flash is actually a high priest of the Speed Force. Okay, if you think about this guy, right? And I'm putting it out there like this, right? He actually is not speeding up, but he's working very, very hard to slow down all the time, right? If you think about this, it's a different way of thinking about stuff, right? But it's almost like the Flash has pent up energy, right? Think about the Flash has a ton of energy inside of him, right? All the time, imparted to him by the Speed Force. Lightweight, light years in terms of energy, right? And the Flash is trying whatever he can, and that's why if you actually look at the comic books, he's constantly vibrating. It's not like the show, The Flash, all right, where he's like, I'm Barry Allen and I'm the fastest man alive. It's not that kind of show, all right? We're not talking about real comic book stuff, canon, right, where the Flash is constantly jittering. He's moving back and forth all the time, right? Because it's almost like he's got so much energy that's imparted to him by the Speed Force. He's got to let it go. Energy can't be created or destroyed. It's just transfer. So Flash has a lot of pent-up potential energy, right? So much so that he can travel really, really fast. Faster than Superman, in fact. Anyways, if you like that kind of stuff. Sorry, I know it's a bit of a digression, but it'll get you to remember this stuff, I hope, right? That's the idea. Think about this. I'm storing a bunch of energy. It's like me, I'm being an energy battery, right? If I pass energy from a external system to an internal system, I've given it energy. It's become a battery of energy right now, right? That energy has to go somewhere, right? And it can be dissipated in different ways. Heat, light, sound, smoke, fire, all this other stuff can happen with that energy, but it's got to go somewhere, right? It can't, or it can stay stored in that box. A good example of potential energy is battery. That's a good energy. That's chemical potential energy, right? So battery is a chemical potential energy that it has inside of it. And what happens eventually over time, the potential energy is transferred from one anode to the cathode, right? It keeps on doing it over and over and over again until the battery's dead, right? But there's pent up potential energy in the anode of a battery, right, over time. And the potential difference, the difference between the anode of a battery and the cathode of a battery, it gives you the voltage, right? So that's the way it works. Batteries are not in any way, we're not going to talk about batteries in this course. That is a whole other course, right, on real physics, okay? So we can talk about, we're starting to talk about these two forces, gravity and spring force. I know I'm going long, guys. I know it's 9:12, and typically I don't go so long, but I have to go long again this week because we've got a bunch more slides, and it's really, really important stuff, and I got to go through it. So you've got this idea of conservation of energy, okay, that we're going to get into. And we can associate this potential energy for a system with any conservative force, right? And what we mean by conservative force, we want to, the force has got to go somewhere, okay? So if I decrease the potential energy somehow, it's going to go to kinetic energy. It's got to go somewhere. So the way it works is this. If I have, there's conservative forces and non-conservative forces, right? And usually non-conservative forces have to do with, I'm moving something, right? I got mechanical energy, right? The change in mechanical energy. Remember, mechanical energy is the total potential energy plus the total kinetic energy. That's the mechanical energy, right? So if I've got a change there, and somehow if I've imparted energy outside of the system, right? I'm giving it energy. Hulk is pushing a bus. The bus is its own system. I'm giving energy to the bus, right? Once I've done that, that system has stored energy. It's either going to move or blow up. Something's going to happen to it. It just can't not do anything with the energy, right? Once I've done that, it's non-conservative forces that we're talking about. Okay, so the work done against friction is greater along the brown path. Brown path? Oh yeah, the brown path. Than along the blue path, because the work done depends on the path. Friction is a non-conservative force, right? Okay. I mean, it's kind of a weird example. It's kind of a weird example, all right? But it's like, okay, yeah, no problem. So, okay, so define, when we talk about conservative forces and potential energy, we define a potential energy function U such that the work done by a conservative force equals the decrease in the potential energy of the system. And that's what we talked about earlier. We talked about this idea of energy transfer, okay? Where once there's no energy, there's no potential energy, the potential energy is gone, that's internal, and it goes to kinetic energy usually, typically, all right? We can say that the conservative force is related to the potential energy function through function f of x, see where it says fx is equal to the change in potential energy over the change in x in the displacement, right? So you can find that total force that we're talking about. This is actually an equation that you can use when you don't have complete information, okay? This kind of equation here. And notice the negative sign here. So again, the x component of the conservative force acting on an object within a system, and this is the key, within a system, okay? It's not outside of a system, it's inside of a system, equals to the negative of the potential energy. So think about conservative forces as something that's inside of a system and non-conservative forces as a system acting on another system, if you think about that. All right. And then they talk about deformation of a spring. I'm not going to go into that for a second as we go through energy diagrams. Okay. I'm just going to skip through this because I want to get to the real stuff that we want to talk about. All right, so here's an example. So here's some examples. Now, there's the examples that we have on the slides right now are the examples that have been done. There's a couple of examples that I want you guys to do for this week, only 2 at the end of the slide deck. All right. So here's one. So let's try and figure this out together. And I put these on here because I know your test is next week. So I got to give you this now, right? A force of 50 newtons acts on the block at the angle shown in the diagram. Yes, I will. I'll put up a formula sheet as well, and you can modify it to hell. It's up to you, right? The block moves a horizontal distance of 3 meters, right? How much work is done by the applied force? And that's the key. How much work is done, right? So we know that work is what? Force over distance, right? Force times distance. Force is 50 newtons. Distance is 3 meters. But we also have to use cos theta because the energy is not exactly along the surface. It's at an angle, right? Think about this. We have some examples where we have a, not just in this case, but we have an oxen, right? And it's pulling something on the ground, right? To kind of, do some farming, right? It's kind of carving, kind of some stuff in the ground, right? To kind of irrigate the ground, help irrigate the ground and plant stuff. And the oxen is it pulling in this direction? Where's the oxen pulling? Notice where it's usually tied, right? Across the oxen's neck, and it's almost horizontal, almost the force, right? The more horizontal the force is, the less amount of energy loss you have, right? If I'm pulling a box up, so I'm dragging something behind me, right? But I'm pulling up this way, right? I have less energy going this way because I'm pulling up this way. But if I pull it down closer to the ground, it's easier. If I push something closer to the ground, I have more energy at the ground level. I'm going to have less energy loss up. Okay, that's what's going to happen here. That's what this is saying. That's why you have this cos theta. So it equals to 150 times root 3 over 2, which is 129.9 joules. Right? So again, work is in joules. Simplest example. Okay? And by the way, some of the stuff on the test is going to be eerily similar to these examples, right? Yeah.
Are we going to be tested on units? Like being able to identify if they're correct or not?
You're going to have a question, and you're going to have possible answers, yeah.
I take my computer, push it over here, and then push it back to where I started. Have I done work this distance? Or
wait. It's displacement, right? So remember distance and displacement. What's the difference in distance and displacement? Distance is the total space, distance traveled. I don't know if my brain's a mush now. I can only think of Spider-Man and the Hulk right now, okay? And Flash. Everything else is out of my brain today, right? But whereas displacement is, where it starts off, you start at the origin, and if you end up back at the origin, the displacement is 0. Therefore, the work is 0, right?
Like you can think about it as if you count it as one motion,
yeah.
If you measure them separately.
If you measure it separately, then if you said, okay, this component of the displacement, if I moved in 2 different time segments,
yeah.
Right? If I said I'm moving your computer to the left, right? And then I measured the work that's done, and then I move it back to the right, right? The total displacement would be 0, but in each component, each segment of that displacement, you can have work done, right? Because you could start off with my initial position will be different every single time, every single segment, right? And therefore, there's work being done, right? But the whole energy itself, the stuff that's happening, if you think about the whole entire motion, then there's 0 work done, okay? Okay, that's example 1. Example 2, okay, this is more challenging, and this is the oxen idea. Calculate the work the bull will perform to push for 2 meters a 10-kilogram box sitting on the ground if the coefficient of friction between the box and the ground is 0.5. Assume that the box is being pulled at a constant velocity. Okay, more difficult question. We have a lot of things that we've been given here. One thing we've been given is 2 meters. That's the distance, right? 10 kilograms, that's the box. And 0.5 for the coefficient of friction. And it's the coefficient of friction. What kind of coefficient of friction is this? Is this static friction or kinetic friction? What do you think? Kinetic, because it's already moving, right? If it was static friction, if the question was worded differently and it said something like the bull is pulling, starting to pull a box, the force of static friction is X, right? The force of kinetic friction is Y, whatever that is, right? X and Y. I should use X and Y. It should be A and B, right? Then, assume the box is being pulled at a constant velocity, right? So what is this thing asking, right? The force of which the bull will push the box will be equivalent to the force of friction, right? Because, again, you look at the normal force. So the way you find friction is the coefficient of friction times mass times gravity, which is the normal force, right, is equal to 0.5 times 10 kilograms, which is equal to 49.05 newtons, right? And it may first appear counterintuitive because you maybe wonder why the reason the box is moving is because the bull's applied force must be bigger than the force of friction, right? And this is only true when the bull starts to push the box and therefore giving it acceleration. But when the bull is moving, the box is at a constant velocity. And the only force that is doing the work is the force of the pull. And let's just zoom in here to see this a little bit more clearly if we can. So we see that this is being pushed, the friction is going the other way, and we have a total displacement in terms of meters, that's the D, right? And if we want to find out the total work that's being done, we can remember this is the force, right? We have 2 forces, the sum of all forces going a certain direction times the distance times cos theta, right? So we have the force of friction times the displacement times cos of 0, right? And cos of 0, that's why it's really good to pull at a horizontal level because cos of 0 is 1, right? Remember? Starts off, well, if you look at the cos graph as 1, then it goes like this and down. So that's why it's really, really good. So again, we have 49.05 newtons times 2 meters, Newton meters, right? Times 1 for this part here, the cos of theta, right? Which is 98.1 joules. That's the total work that's being done in this case. Does everyone understand this? Because if you don't, then it's going to be something that you're going to be surprised by on the test because you're going to get something eerily similar potentially on the test. You're going to see a question like this. All right. Example 3. Calculate the amount of work done by pulling a 1,000-kilogram brick, a gold brick. 1,000 kilograms. Hulk has to push that one for sure, right? For 3 kilometers. Actually, you can probably get someone like, Luke Cage. He can probably push a ton, no problem. That's like a metric ton. For 3 kilometers, I don't know about 3 kilometers. He might be like really exhausted by the end, right? He can't push it to Netflix. He's done. Netflix is over with Luke Cage. I know, right? I know. It's too much for me. 1,000-kilogram brick of gold for 3 kilometers on the ground at an angle of 10 degrees. Okay, at an angle of 10 degrees. If the coefficient of friction is 0.25, assume the box is being pulled at a constant velocity. What is the total work being done? Right, because that's what we're looking for. Again, if you think about this, the force of the pull is equal to mu times mg, mu being the coefficient of friction, times the normal force, mg, right? And now this is interesting. It says over cos theta plus mu sine theta. Why? Why is this the case in this case? Right? We're trying to find the force of friction, right? And if you notice, we have this situation here, right? Force of the pull is at an angle this time around. Okay, so friction is here, but why are we dividing it by cos theta plus mu sine theta? Why? I know, but where are we getting this from? Like, it's like, you know, force is equal to ma, right? What's this? What the heck is cos theta plus mu sine theta? Why? Why here like this? Anyone know? Well, if you think what we're trying to accomplish, we're saying that, and how else would you frame this? That's the other way to think about this, right? So the kinetic friction, like we have this way, right? That's the kinetic friction on the ground, right? But we know that we're going to multiply that by cos theta, right? And if you think about it, when we try and find out the force of kinetic friction, right, there is a y component to this thing, right? There's a y component and an x component. The x component is pulling this way, the y component is pulling this way, right? And when we put them together, cos theta, mu sine theta, right at the bottom, we get something that looks like this. We get like 0.25, which is the force of kinetic friction, times 1,000 kilograms, times 9.8 meters per second. That's gravity, right? And we're dividing that by cos 10 degrees, because that's what we said, 10 degrees, plus 0.25 to sine of 10 degrees. And if you think about that, we get some kind of, you know, force of 2,380 newtons. But why this? This is the situation where we have to look at. Which formula was used to get us this? Something over something else, right? And this is where it becomes unclear when you look at this thing. If you go back up, let's take a look at what we're looking at. We're looking at forces, right? Is there some kind of kinematic equation or something like that that can help us out with this thing, right? Because it's really a force of the pull. Now, if I was going to block it up for a second and think about this in my head, right? And I would say, calculate the amount of work done, right? That's what I want to find out. I need force over distance. That's what I need, times cos theta. That's what I really need, right? So I have 1,000 kilograms brick, right? If I didn't have the coefficient of friction, so I don't have that, let's just say, right? So I have this mass, right, as an example, that I'm pushing for 3 kilometers. So again, I have a mass that I'm pushing for 3 kilometers. That's the distance, okay? But mass is only one part of force. I need acceleration, right? F is equal to ma, right? I'm pushing it, right? And I don't have all my information here, right? If it's a frictionless surface, how would this change the problem? I have no friction. Yeah.
Well, if you're already moving, you'd be doing no work, no acceleration.
So no acceleration, right? If I have no acceleration, I'm moving at a constant velocity, right? You're saying there's no work?
Force is mass times acceleration.
Force is mass times acceleration, right? Force is mass times acceleration. So if I'm not accelerating somehow, right, then I'm not, there's no force. No force, there's no work. That's the bottom line, right? So that's interesting. If it was a, and that makes sense, right? Because if it's a frictionless surface, then I can just push it and I would do no work. It would be nothing to do, right? I mean, literally, it would be like floating, right? Like I'm in space. Whoop, I got no energy, and it's like a micro amount of energy, because it's still some kind of energy that I'm part, but a really small amount that's negligible. Let's put it that way, right? However, the force is coming from the friction that I'm getting on the ground, right? Because then I have to push it to counteract the friction that's going the other way. I have to apply forces, right? So that's the one thing you have to think about. I have this kinetic, friction going the other way, and if I think about friction, it's the force of the coefficient of friction times gravity, mass times gravity, and that's my negative force going the other way, right? So I've got negative forces on the x-axis, right? And I got positive forces on the x-axis and the y-axis because of the angle. That's what's happening here, okay? And the reason why it's an inverse relationship is because you got this friction only on the x-axis, but not on the y-axis. If I had force and friction somehow on the x-axis and the y-axis, this might be a totally different picture, right? But where again, we're going to come back to this, but where again is this equation coming from? Okay, we have to figure out how this came to be altogether, right? Otherwise, once we have this 2,380 newtons, we know that it's newtons over distance, right? So we can sit there and say, okay, here's newtons, here's 3,000 meters, which is 3 kilometers, times cos of 10 degrees, which is something in the realm of 7 times 10 to the 6th joules, right? 7 million joules, right? Of energy or work that we're going to be pushing this thing, okay?
Why can't you just take the upwards force of the ground, 9.8 meters per second, and then subtract the upwards force of the push from it? So that
you could. There's different ways. Again, you can do things in different ways. Okay, when doing a chin up, yes. Say that again.
Why you
Because when it comes to work, first we're calculating force, right? Here we're calculating work. Totally different. You need to calculate force before you can calculate work, right? Force is being done on an angle, right? And when force is done on an angle, you have to use cos theta, remember, or cos whatever, right? Force is not being done straight off. If you didn't have any, if it was just perfectly straight, like the oxen example, you wouldn't need this, right? Angle. Right. Yeah, I know. It's the way it's been written. Yeah. So anyway, so if you notice, it's just a straight equation. So work and force are totally different things. We need to calculate force in order for us to calculate work. This one?
Why is the friction in relation to gravity?
Because remember, if it was frictionless, no work. No work because there's no acceleration.
I mean, why is in relation to gravity? Not only for mass and speed.
Well, friction, remember, the more gravity there is, let's suppose we have gravity and we have the force of kinetic friction, right, is related to gravity because gravity is pulling you down. Gravity is trying to seat you on the ground, stop you from moving. If what?
It's the movement of the horizontal side, not the vertical.
But there's still, what's happening is you're still being drawn down, right? So because you're being drawn down into the ground, the force of kinetic friction is trying to stop you, right, from moving. If the ground was frictionless, then we wouldn't care, right? Frictionless means there's no coefficient of kinetic friction, 0, right? And if that's the case, how much work is being done? 0, right? Potentially. Let's go down to this one. When doing a chin up, an athlete lifts her 55-kilogram body at a distance of 0.25 meters in 2 seconds. All right, what is the power delivered by the athlete's biceps? This is interesting. So we have power, right, is equal to work over time, right? And we have this work, the force of gravity times the displacement. Remember? That's what work as gravity is. Times cos of theta. But remember, cos of theta is going up and down in this case, right? So we have 0 on when it comes to, it's 1. Cos is 0 because it's up this way or this way, it's 0, right? In this particular case, because it's going up in the same, it's moving in the same axis as the work, right? So there is no, we don't have to calculate cos theta, right? Over time. So we can fill in this is a simple one. We fill in 55 kilograms, right? Times 9.8 meters per second. So force of gravity and mass times gravity times 0.25 meters. That's the total displacement. So that's the work that's being done over time, 2 seconds, which is, again, 67.375 watts. Yeah, it's kind of weird that the athlete's actually projecting some kind of energy this way, but that's what's happening, right? And by the way, where's this energy going? Heat, right? Because the athlete's going to get hot, right? The athlete's generating energy, right? Sorry, I got just a blink of the Matrix for a second. Anyone ever see that old 1990s movie, The Matrix, right? Where, you're all batteries and stuff. There's diminishing returns, when it comes to the battery, right? So, what was that?
I don't think it's a good plan.
It doesn't make sense, right? Because unless you're doing work, if you're doing work, right, all the time, and it's leaching heat off you, right? So you're eating and doing work, then it makes sense. But if you're just sitting there and lying down, right, you're not doing a lot of work, right? And all you're getting is this micro voltage from your, from your body. Your body, your entire body gives off this micro voltage. It can be measured, right? When people put electrodes on your head and all this kind of stuff, right now, if they were to do it, some of you would be, there would be flat lines happening on some of you, right? No, I'm joking. There'd still be some kind of alpha waves happening on some. If some of you are in delta sleep right now, I can see you right now. There's a couple people who are here, right? But at the end of the day, right, what you have is this micro voltage is coming off your brain, right? It's happening. We have it all the time, but it's diminishing returns. We don't have a lot of voltage, right? However, if you do a lot of work, like this athlete, that would be better for the matrix. If the matrix showed these people like doing something inside like their little bubbles, right? They're acting out their stuff. That would be energy, right?
Black Mirror episode where they have the guys generate money by
running a bike, riding a bike. That's perfect because that's generating energy, right? All right, there's a couple more examples here. These ones I want you guys to do on your own. We'll do them inside of lab, and I want to work these out with you because we need to do this stuff because of the test next week. So in lab, I'm done for today. But in lab, what we're going to be doing is we're going to be talking about review. I'm going to review stuff from this whole module this week, as well as talk about these two questions that are going to be due by Friday. Okay? Yes?
In the example before this,
yes.
I still don't understand why you're dividing by cos theta.
And this is where we have to kind of explore this. I want to explore this in lab with you guys and go through I want to go through all the equations to find this out.
Did I understand basically what that's doing is lowering what the force of friction would be because you're pulling at an angle?
It's actually a skipped step. The calculations here are remember what force is equal to mass times acceleration, right? So mass times gravity, that's one part of the force.
Yeah.
But you also have a competing force that's happening, right, when it comes to the other pieces, which is the acceleration due to gravity, or sorry, the acceleration on an angle, right? So we have to look at this stuff. We have to look at the kinematic equations, and you're going to see that this is a middle step. We're not seeing the first step, right? How to get to that equation, right?
Because I'm just wondering why it's dividing and not placing.
Well, if you also think about it this way, we have mu over mu, right, on one of our examples, right? And then we have this cos theta. So we have to kind of look at this and say, how can I derive this one, right, to get the force of the pull, and why is it this way? Okay, so we're going to look at that in lab, because I want to talk about this with you. Okay. Any other questions? Yes.
I'm still confused the energy work and there's no way. Obviously, there's no displacement. There's no highest but why? Can I still say there's no energy? I hope there's no displacement.
Okay, so again, what's the difference between energy and work? Let's go back. Hold on a second, Victor. By the way, I need you guys to stick around one more second. Victor's going to have a small announcement for us. Not yet, Victor, while we go back. That he wants to talk about. Let's just go back to this. That makes it easier. So if we go back up to the top, which is what we talked about, right? Way to the top. Some of the first things we talked about is this. So power is work over time. And we want to try and figure out what energy is, remember? So we talk about energy of a system, and we talk about different kinds of energy, right? That's the first part. And we look at work as defining a type of energy, right? Again, we also said that mechanical energy is potential energy plus kinetic energy. That's what we said, right? But down here, we define work in general. We say that work is equal to Newton meters, right? That's energy. That's the energy of that. We define work as Newton meters. So if I exert Newton's force, but it doesn't move anywhere, zero work, right? If I define, I want to move something, I move something, but there's zero force. Somehow it's moved, but there's zero force somehow, right? There's zero work. It's hard to find that relationship. How are you going to do that? Huh? Zero, well.
Because when you're talking about energy, you can't talk about just energy.
Yeah.
You have to talk about a specific kind of energy. So if it's not moving, there's zero kinetic energy.
Yeah.
But let's say I'm holding my phone out here. It's not moving, it has zero kinetic energy.
But it has
Potential energy.
Unleash your phone's potential.
It
Yeah.
depends on the mass of object. I put the same force on.
Actually, the reality is, if it's moving, it's got kinetic energy somehow, right? It's got kinetic energy, whether it's moving on a frictionless surface or not, right? But however, did I do any work to get it there? That's a different question, right? Anyways, we got to end it now. I got Victor to come in. We'll talk about it during lab, right? And remember, next week, just for people who came in late, there is a test next week. Test 2 is coming up next week during this time. There will not be a lecture during this time next week. We'll just be doing some review and answering some questions. For those people who need to book rooms for next week, because some people have that requirement, please do it this week. So that way you have a room to do your test in next week.
And the test will be on our normal lab period.
It'll be during your normal lab. So it'll be on Tuesday after this class, on Wednesdays from 10 to 12, and on Fridays from 8 to 10. Okay? Like your regular lab time. Okay, that's all I want to say. I will make an announcement on Blackboard to that effect as well. And you also will be getting your own cheat sheet that you can modify, like we talked about. Okay.